Welcome to our end of semester problem presentation. We are Team J and K problem presentation. The problem was a service company operating at an office apartment building offers workers to service working services. The workers work in shifts and are divided into groups. So each group reports to its office management, and the group members should not interact, but the group supervisors interact. The supervisors report to a general caretaker, and there is a relationship between there is a duplex relationship or kind of communication between the supervisors and caretakers. So we'll go through the solution is to come up with a logic solution on how there will be a perfect flow without any confusion. For the solution, we came up with the universal set U, everybody in the building. That is all the people working in the building, and that is the caretaker, supervisors, and the other members. The relations between the parties, we needed to match every party with each other. So firstly, supervisors, the related supervisors to workers and cooks. So the supervisors related to the workers in that every supervisor, one for each shift, that is, can relate or interact with the other supervisor, but the supervisors cannot interact with the groups that they did not supervise. So this was represented by, for each shift there exist groups, whereby the groups of one shift are not equal to the other. For one group does interact with the other, represented by not equal to. From the caretaker is a singleton set. So his relationship with the supervisors, here we see that the caretaker can relate with the supervisors and vice versa. However, in this relation, the caretaker is able to interact with both the supervisors' shifts. That is the individual members. So in the workers, we decided to name the individual groups. For example, the first group names of the first shift, are Simba, Mamba, and Ndovu, and the names of the second shift are Savannah and Amboseli. Those are the names that we chose to make the work easier and to reduce the complexity. So as you can see there, we have the first shift 10 members, groups of 3, Simba, Mamba, and Ndovu with the respective members. Second shift the same. Going down to the cooks. The cooks are 4. We have 4 cooks. And so in the cooks we did not go deep as we anticipated, because we thought that it was pretty simple. They are to work as per the normal working hours. They don't have shifts, and they still report to the caretaker because it's the overall acting boss. So supervisors, first and second shift respectively, we have Collins and Mutua. Those are the 2 sets. The individual groups and shifts are disjoint sets. For example, Alex can only be in group Simba in shift 1 under supervisor Collins. So when on the caretaker consists of the universal set. That is, he is in the universal set. So you don't. The caretaker has a codomain of sets containing the members of the shift 1 and shift 2. Not the codomain of shift 1 consists of sets of all the shift 1 group members. That is Simba, Mamba, and Ndovu. The codomain of shift 2 consists of a set of all the shift 2 group members. That is Amboseli and Savannah. Yeah. So the rules of engagement are pretty simple. Groups should not interact but report to their supervisors. The supervisors can interact but they only have access to their group. So the caretaker can interact with the supervisors and group members only. It's more of a really good communication. The desired solution is that Alex was in group 1, shift 1, and the supervisor is Colin. So the question was, how do you represent they do not interact? Will it be a relation or a function? So how we went about it, we used a relation to find the members of shift 1. For example, let S1, that is shift 1, group Simba, be shift 1, group 1 in Simba. So the same for the 2 shifts. Those are the so a relation between shift 1 Simba and shift 1 Mamba contains members of shift 1. The same explanation goes to shift 2 members. So on the next page, and also the caretaker relates to all other staff, that is supervisor and the rest of the group. This also can be described as one-to-many relation. So I'll welcome Ken to take us through the project flow. So,
Okay, thank you, John. My name is Ken Duati, and this is the project flow. We can see that there's a relation between the individual groups and the supervisor, and then there's also a relation between the supervisor, the two supervisors, and the caretaker. So the arrow shows that this is just a simple flow of that is a relation between the Simba group and the supervisor, as well as the other groups. The other important thing to note is that it's different. When we started with the solution, we saw that we said shift 1 members should not meet or with the shift 2 members. So with the line dividing the two parts, that is just a simple solution to illustration to what we meant. And here we have representing the groups as X, representing the supervisors as Y. So now this is the general part, not the individual groups, but we have the general view, representing the groups as X, representing the supervisors as Y, and then representing the caretaker as Z. We have a function, the way I've said, that maps the groups which are X to the supervisors who is Y, and then there's also a function B that maps Y to Z. And then since we had described that the caretaker will be a one-to-many relation, we have to show how they relate to the smallest unit, that's the groups. So using C, we have a function Z that maps, C is a function that maps Z to X, and here is how it's illustrated how it works. And now on to the other part, we have given the supervisors. This is how we're showing how we start from the groups relating to the supervisor, and then the supervisor will relate to the caretaker. But for now, let's show how the groups will relate to the supervisor. So we have Simba, group Simba, and up to Ndovu. There's a function A that maps this group of Simba to the codomain of shift 1. So there's a domain of these three groups, and then it maps all of them to the codomain of shift 1. And here is the explanation. As we had seen, A maps G to S. So G can be a general or general representation of the three groups, but narrowing it down to the individual groups, we have that S1 will contain group members of Simba, Mamba, and Ndovu. So how do we know that someone is present in shift 1 or he is not present in shift 2? If X exists in S1, so X can be an individual member. For example, as we stated, the members are we have Alex and so on. So if Alex is in that codomain of shift 1, that shows that he's a member of Simba, Mamba, or Ndovu, and he's in shift 1. If you have a foreign name and the foreign name is not in the set of S2, then X is not in S1. Yes. So, and then we have there exists two shifts, as we had stated. There's a shift 1 containing of these three groups, and shift 2 containing of these two groups. The function P maps the groups Simba, Mamba, Ndovu to S1, from Simba, Mamba, Ndovu to S1, that way. And then we have another one Q that maps Savannah, Amboseli to S2. And then there's a function R that maps S1, shift 1 to C, and then shift 2 to C. So, and here what we are trying to achieve is showing the relation between all the members, where we said that the C now, if this is the domain and this is the codomain, and this, if Savannah, Amboseli form the domain, and then S2 forms the codomain, respectively in relation to S1 and C, S1 will form the domain of, and then C will form the codomain. So the codomain of C consists of all the members of shift 1, which includes members of Simba, Mamba, Ndovu, and the same case to shift 2, which contains members of Savannah and Amboseli. So that shows how C contains all the members and how it relates to the other group members. So, and there's also a problem that we had we wanted to illustrate, and this was how if the shift 1 is on, shift 2 must not be on. So that relation has that concept has to be shown, and we decided to use logic gates to illustrate the concept, where we have instead of stating mamba, ndovu, and simba here to reduce the complexity so that we can be able to view it easily, we decided to use G2, group 3, and to illustrate the individual groups of shift 1, and then we have A1, A2, A3 representing groups of shift 2. So this is how we are going to represent that. The final solution shows that if shift 1 is on, shift 2 is not on. If shift 2 is on, if shift 2 is on, shift 1 must not be on. It's like an on-off relationship, and it was achieved using logic gates. And as we had explained here, I have explained on the names, and we have used the AND. This is an AND gate, and this is an OR gate, and this is still an AND, and this is an OR gate, and we have also used an OR so that we can achieve the relation between something that is on and then the other one is not off, and then the other one is off. So in conclusion, our problem flow consisted of several parts, and as we wanted to break down the complexity of the structure, we decided to use symbols such as S1, S2, representing the shift 1, shift 2, and then the individual groups having their names, and then the names have members under them. And we had the caretaker acting as the overall boss, so that we can have a general point or a reference point, so that we can form the universal set. And we used relationships and the functions, mapping from one group to another, mapping from one set to another, so that we could achieve the desired goal. Thank you. And in case of any comments, please feel free to contact us. And thank you for taking the time to listen to what we have.